Um, I'd like to start my talk by talking about, out of the three, fight, flight, or entrainment, I'm going to start by talking about entrainment. And so I have a video to sort of demonstrate what I'm talking about. We have 32 metronomes on this flexible table, and they're all set at different frequencies. And they get started, and it basically just sort of sounds like some noise. It doesn't really sound like anything meaningful. But after a couple of minutes, 2 or 3 minutes, we see this sort of synchronized behavior, and so that's sort of what I'm talking about when I say entrainment. We have multiple oscillator systems interacting with one another, and they're all sort of moving in an entrained behavior with one another. Now, humans can actually do something kind of similar to this. So here we have a bunch of people on a swaying bridge. This individual has a very unique frequency, but presumably everyone kind of chooses some frequency in the beginning, but very quickly they can learn to coordinate their efforts and sort of start making the bridge sway. Maybe it's sort of some implicit coordination because I don't think they know that they're doing it. And then in this video, maybe we have a more explicit coordination. People have been training to sort of do this sort of rigid looking gait. And the only reason I show this video is I just want to sort of illustrate the oscillatory behavior of human gait and just how you can think of human gait as an oscillating system. So you can also think about that in a more natural looking gait, and then the question might be, why do people pick particular parameters to that oscillation as they do? So I'm going to propose that we start a drinking game with this one. So every time you see the word energy or optimization, maybe you just lift that beer and take a swig. But the reason it comes up so often is because it works really well, right? So we can make these sort of predictions and find that humans and animals do tend to move in ways that seem to be minimizing energy. But what's we know a lot less about is maybe how people or animals do that in real time. So how is that optimization process working? This next study is one of my favorite studies. They looking to kind of get at that question. So they have a knee exoskeleton providing resistance at the joint, and that resistance is just a function of the frequency that the person is choosing. And so they can do things like penalize certain ranges of frequency, right? And maybe drive their minimal cost solution in a different direction than they would have normally picked. And indeed, with enough exploration, individuals were sort of on average able to figure this out. But that's a very specific localized perturbation to the joint. And we were interested in a similar question, but maybe in terms of a more a perturbation more at the body level. So can people adapt, for example, to a vertical oscillating impulse applied to the torso, say as a proxy for the center of mass? And then when I say the word adapt, that's pretty vague. So raise up your beer glasses and say with me, energy optimization is what I mean by that. So here's a really simple trajectory optimization model, point mass body, prismatic leg actuators, and we're optimizing the mechanical work of, or rather the integration of mechanical power of those leg forces as well as the time rate of those leg forces squared. And then we simply apply that oscillating force to the center of mass as a sinusoidal wave. We match the frequency to the stepping frequency of the model, and then we can play around with variables such as magnitude or phase. So this is an output from the model of energetic cost as a function of that phase. And so when I say phase, I'm referring to the time lag between the peak of the oscillation force to the peak of the leg forces. And basically, it turns out that the minimal cost solution is when you have the system in phase such that you get some help of the positive impulse on your body to help redirect your body during the step-to-step transition. Conversely, if you have a downward force, it's pushing you down into the ground while you're trying to push off of the ground, and so it's more costly. And then we can look at magnitude, and it basically turns out that it's more or less the same cost relationship. It just sort of scales the fluctuations appropriately. So notice how there's one minimal cost solution in that phase domain there. And so that means that if you want to take advantage of that with each successive step, you have to be hitting that particular phase every time. The problem is, such as in this example, if you have different frequencies that are not equal to one another, then the phase is constantly changing in time, so you can't always manage that same phase. On the other hand, if you have two pendulums that are operating at the same frequency, then they do have a constant phase. And so the point I'm trying to make is that you really need to think about frequency entrainment if you want to sort of collapse into a particular phase that you're interested in. So the question being, can people learn to do that with some sort of oscillating impulse to their body? And so the physical setup we have basically a person is walking on a treadmill in a body harness. We have the motors in the lab frame pulling on this pulley cable system, and as the motors pull, it creates a tension in the harness and pulls them up and down as they walk. So basically, I'm just prescribing an open loop current control with just a simple sinusoidal input to that. And then, as I say, the motor forces creates the tension in this pulley cable system, and the person feels it on their body. Now, there is some interaction here because essentially the actuators are sort of hanging off your body as you're walking. And so if you have some vertical motion in your step, then you're changing the state of the motor itself. So you're changing its velocity, its force, and its mechanical power. So there is that interaction in there. Now, the type of test that we're doing is called a magnitude ramping test. And it's a way to probe at how sensitive subjects are to this entrainment. So here in this plot, we're looking at normalized frequency over time. The solid line is preferred step frequency of the particular subject. The dashed line is the motor frequency that we're prescribing. Notice the motor frequency is always displaced from whatever the preferred frequency is. And so again, that's how we're going to try and test to see if people can figure that out. And so some of the different conditions we prescribed were motor frequencies plus or minus 3, 6, or 9% away from that preferred frequency. So basically what happens is they have a couple of minutes to walk on the treadmill with the motors off, and then the motors gently start up with a very soft oscillation and continue to grow in amplitude over time, and then we sort of sustain that amplitude at a higher value, and then we just cut it off and let them walk for another 2 minutes with the motors off. This is fake data, but it's like something like we're sort of predicting to see. So people start off with their preferred frequency when the motors are off, and then the oscillations start up, but maybe they're light at first so the person doesn't care about it, or maybe they don't even know what's happening. Eventually, at some point, they do care about it. They drift their frequency, and they entrain at that new frequency, and then the motors turn off, and maybe they return back, or maybe they don't. So one thing we can do is we can determine the point of initial entrainment, and then we can determine the amplitude prescribed to the motors at that initial entrainment. And then, again, that gives us a sense of how sensitive people are to this. So this is fake data. This is real data. In the top, we have the condition where motor frequencies are 9% greater than preferred, and in the bottom, they're 9% lower than preferred. And so they sort of look similar to the fake data. Obviously, there's more noise and more little nuggets of things happening, but the general shape is there. And then, as I said, we can locate that point of initial entrainment for individual subjects. And when we do that, I plot it on the y-axis, so it's prescribed motor amplitude at that initial entrainment as a function of how far away the motor frequency is from the person's preferred frequency. And so basically, we have a positive slope, meaning that the further away the motor frequency is, the more amplitude in the motor you need before you see the person start to respond. That's fairly intuitive, but something that's a little more interesting is if we break it up into two components. So now we're looking at the trials in red are when the motor frequency are higher than preferred frequency, and then the trials in blue are when the motor frequency are lower than preferred frequency. And so basically the idea is that people begin to entrain more quickly when those motor frequencies are lower than preferred. So for some reason, they're more sensitive to that. Now, all those data I just showed you are for 8 out of our 10 subjects who sort of on average were able to find some entrainment at some point in the test. The other 2 of the subjects consistently did not, and they did not in distinct ways. So the first one I've dubbed as a sort of fight response, and so this subject basically tried everything they could to stay at their preferred. They were just stubborn and didn't want to change, even when they were knocked off for a second or two. But what was also interesting about that is that they claimed that, oh, they really felt like they were in tune with what the system was doing. So take that as you will. And then the other one we had was this flight response. So this subject was interesting. She actually mentioned that when she did allow the oscillations to drive the motion of her body, it made her feel sort of anxious and uncomfortable, maybe like she didn't have control over what her body was doing. And so she would sort of actively try and avoid that by exaggerating her gait features. So she's just almost doing like a power walk there. And that's not just because the motor frequency is high. It's the opposite, actually. She's trying to leave that frequency. So then you can compare that to the video on the right of someone doing some sort of typical entrained behavior. It's it's pretty clearly a much more casual gait. Yeah, and then so yeah, this idea of subject personality maybe playing a role that Monica mentioned last night, the brave bird versus the shy bird. In this case, we do have a couple, I would say probably outliers that sort of didn't follow that regime. But I think this could be an important thing to think about sometimes when we're thinking about, for example, designing an exoskeleton or a prosthetic. What are the different things that determine how a person perceives what their interaction with the device should be? Anyway, with that, I'll take any questions you might have.
Any questions?
So you started out with phase entrainment, and here you've done frequency entrainment. So what did you learn about phase entrainment by the same experiment?
So phase is a bit trickier, and the issue is, as I mentioned before, because the motors are hanging off the body, there's this inertial effect that's always out of phase with your motion. And so in the same signal of force that we recorded, we have those inertial effects in there as well as whatever the motor's doing to pull against that. So it's a little bit harder to tease that apart. It's one thing that I want to do going forward. And then the other thing we want to do is we want to do like a constrained optimization where we basically sort of align the motors in a particular way depending on what the person is doing, so we can capture metabolic data and maybe mechanical work data on, basically recreate that cost over phase that we had for the model.
Can they see this motor moving in front of them?
Yeah, so I had a slide about this, but I took it out because it was just going too long. So we had a curtain in front of the motor so they could not see it, and then we also gave them headphones and it had some ambient noise sort of somehow blocking out some of the noise.
What were the instructions given to the subjects? Like, were they asked to try to match the frequency, or like try to walk at their preferred frequency, or is this like a rhythm sort of thing?
Yeah, so as with most of the talks, pretty vague. I did try to guide them a little bit. So the general instruction was walk in a way that feels most natural, whatever that means to you, or in a way that feels like you have less effort or something like this. And then I'd also say, what we don't want you to do is sort of try and game the experiment, figure out what you think we want you to do, but just do whatever feels natural.
Any other questions?
We did some hopping experiment in which we asked the people to just hop with their preferred frequency, and then we used metronome with the same frequency, and then we checked how variance is different in these two experiments, and the variance was higher when we used the metronome.
Really?
Yeah, it was kind of extreme. This experiment that you have done, I don't know how we can explain those experiments, the results, and did you find something similar, or maybe with the other two subjects you can, I don't know.
Yeah, it's a really interesting question. I think I'd want to probably think about it more. What I can say in terms of variance is, so I showed you one test today, but we've done a few different iterations of the test, and I've given presentations on it. And some of them, the variance drops to almost zero when all the subjects are entrained. And so it really seems like there's quite a bit of variability, and whether that's partly because they're just being thrown about or or if it's a control affect, I don't know. But it does seem like when they do figure out some sort of entrainment solution, variability drops very low, and they're able to sort of really hone in on that.
Can the next speaker, Sun Moon, come up? And then Art.
How did you get those? You did show some phase results. How did you get those?
The phase results I showed were all just outputted from the model. Yeah, so that's just constraining the model at a particular phase and then plotting the cost.
Any other questions? One more?
So you couldn't interpret the phase, but was there consistency in the phase between subjects?
For the most part, yes. I can't say to what extent because I have to look at the data more closely. Yeah, so it's something that I want to look into. But I would say in general, yes. It did seem like there was some sort of clear pattern of what people were doing.
Victor?
Carol Welker, Stanford University. So with your staircase method, you kind of ramped up to see when they would entrain. Would you expect to get the same result if you ramped back down afterwards?
So I did do something similar to this. This was sort of one of the other tests that I did. Although I didn't ramp up and ramp down with amplitude, I ramped up and ramped down with frequency at a constant amplitude. And so the idea was to start where it's really easy to entrain, at their preferred, and then see if I can drift them away and bring them back. And then some people would follow it all the way, some people would follow it some way up, and then they would veer off when it became too far of a frequency, and then they'd catch it on the way back down. But usually when they catch it on the way back down, it was a little bit lower than on the way up.
Maybe one short one while I'm getting set up. Greg?
The cost function that you used had a work dot plus a force dot term. Can you talk about why you chose that particular function?
Yeah, so the force rate cost, frankly, a lot of it's just due to convenience. The optimizer converges more easily when you have some sort of smoothing function like that. So part of it's so I can run a bunch of these optimizations to get all kinds of cost surfaces with every parameter combination and this sort of a thing. And then I don't mind doing that too much because there is evidence emerging that this force rate cost might have a real metabolic penalty. So some of the work that Art and his group were doing, showing that.
I think it'd be cool to eliminate one or both, eliminate one term, check the optimization, eliminate the other term, check the optimization, and then check it with both in there.
Yep.
So that when you eventually collect your data, your metabolic data, you can say something about F dot versus W dot.
Yeah, I think that's a good idea.
Was that your speaker?